Our speaker is Laura Tolos from the Institute of Space Sciences in Barcelona. Her PhD is from the University of Barcelona on strange mesons in dense matter, following which she was a Humboldt Fellow at Frankfurt and then GSI, assistant professor at Groningen, and then a couple more positions, including a Heisenberg Fellow at Frankfurt, and is now a tenured researcher at the Institute for Space Sciences since 2020. So thank you very much for speaking with us today, Laura, and I don't see slides.
Okay, yes, thank you. Thank you very much for the invitation. So I'm just going out to share slides. So yeah, okay, let me put it, sorry, in full screen first. Full screen, and then I share again, and I hope now you see it. Is it? Yeah?
Perfect. Yes, fantastic.
So thank you again. I mean, I say for the invitation, I'm really happy. I mean, to be able, to talk. I would be even more happier if this was face to face, but okay, we are in this situation nowadays, right? But anyway, so what I'm going to talk, as you probably read in the announcement, is about strangeness in the lab and stars. So I'm going to try to give, a bit of an overview of things related with strangeness. And maybe I will not give you much detail. So I just want to give you maybe the main concepts. But of course, if you have questions or you don't understand something or you want more details, you can also stop me and ask anytime, okay? So as I said, the title is Strangeness in Laboratory. So basically, I put here two nice pictures, okay? Just showing you, where strangeness might appear. So the first one is what they are called hypernuclei. So I will discuss briefly, about hypernuclei. So it means nuclei that contain one strange baryon. And I will, is a place where you can test the interaction of the strange particles, okay, with others that don't contain strangeness. And of course, there is also neutron stars, where probably it's a really interesting object, a stellar object, but we don't know much about what's going on in the interior, okay? And then one of the interesting scenarios that you might have is that you have particles with strangeness. Of course, strangeness means, strange baryons, strange mesons, strange quarks. So it's a very generic word. So since I'm of course not an expert in everything, and I'm more expert, in maybe in mesons and baryons, I thought let's focus on something, and this is going to be on strange baryons, basically hyperons. Okay, the name of hyperon is a baryon with a strangeness. So I'm going to, as I said, mention a few things about hyperons in the laboratory, and also then I will move in the second part of the talk to stars, in particular neutron stars. So, I mean, I put here a reference that we did together with Laura Fabietti. She's an expert experimentalist, is an expert on strangeness. And yeah, if you're interested, you can just look it up here. So what is going to be the outline? So first of all, to introduce you what hyperons are and actually where to find them. Oops, I went too fast. Where to find them. And then I will move to trying to show you what we know, as again, very briefly, on interactions of those particles. Usually they are noted with this Y, and interaction with them with nucleons or the interaction among them. Okay, so I will mention a few things we know from these interactions experimentally, and then I will move to the theory part and I will present you a couple of examples. Then I will move to hypernuclei. So it's a few body system, in the meaning that you have a hyperon or maximum two hyperons that see a few nucleons, right, from the nucleus. And then I will give you again a couple of examples of information we have from the interaction with hyperons and nucleons. And then now I will move in the next to matter. So then it will be like a many body system. So an infinite system in particular, and to explain you a bit what are the things that people or researchers have been doing in matter. And of course, finally, I will talk about the stars, as I said before, because as I said, is a place where you actually could find hyperons. And then I will mention, well, a puzzle involving hyperons and a few features of those hyperons in neutron stars. So let's start with what are hyperons and where we can find them. Well, actually, hyperon, as I said at the beginning, is a baryon, and it contains one or more strange quarks. So here is a table of hyperons. So you have lambdas, you have sigmas, you have cascades, and you have omegas. And if you look at the quark content, this will be the quark content. So you can see that you're moving from one strange quark to two strange quarks and three strange quarks. Of course, these particles have, well, depending on, the structure of them, they have different isospin and different spin and also parity. And the nice thing, or let's say the one of the features is the mass of these objects, okay, these baryons. And actually, if you look at the mass, for example, of the lambda, you can see that the mass is not so different as the nucleus, okay. It is larger, of course, because we expected that already because of the strange quark. But okay, as you will see, is not so different of the neutrons. If you look, for example, at neutron stars, you will see what I mean by that a bit later on. So one place, as I put here, is on Earth, for example, on hypernuclei. So here is a picture that I took from a Zoom. Basically, it's like a nucleus that bounds a hyperon. So this is what we call hypernucleus. And actually, this is a chart of this hypernuclei that we know. So you have here hypernuclei containing a lambda. So you see, well, a few of them, of course, not all of them. Actually, there's about 40 or maybe even more nowadays of different hypernuclei where they have a lambda. But if you move in the vertical axis, you actually have already results of nuclei with two lambdas, like helium, beryllium, and bohr, for example. And here is like different reactions that you can perform in order to obtain this hypernuclei. So this I will mention later on. And the interesting part, of course, is why this hypernuclei are so interesting. Well, because it gives you a new spectroscopy. So it gives you a new chart of nuclei, including strangeness, of course. And that allows us to get information on the strong and the weak interactions involving strangeness, okay, involving hyperons and nucleons. So this is on one side. Of course, on the other is these neutron stars. So neutron stars, as you probably know, are one of the most compact objects in the universe. So we are talking about objects of 1 to 2 solar masses and radius of around 10 kilometers. Of course, the radius is something that nowadays is becoming really exciting because there are measurements of these objects with the mass and the radius. So this is thanks to NICER, then we are having this new data. So, but in any way, one of the largest part of the star, you can see this kind of a configuration of an onion. And in the center of the star, we actually don't know what it's in there. But of course, depending on what we have inside, the features of these objects, the mass and the radius that I was mentioning, we will have a different prediction for those, okay? And then for it is interesting to really know, what you have inside and then compare with observations. So the different possibilities are shown here. So you might have, only quark matter because those are densities very high inside the interior of these objects. And of course, you could also think about having mesons and baryons. So you might think of having hyperons, or even not hyperons, but you have mesons like pions and kaons, and then those, since are bosons, will condensate, and of course the features of those objects will be completely different. This is, of course, assuming that you have different scenarios for the interior. Of course, you can think that except for the very outer layers of the star, you don't have a confined matter, but you have basically strange quark matter, so up, down, and strange. And then the features of the object of this compact star will be completely different. But in my case, I'm interested in, assuming that we have hyperons in the interior. So to get information maybe on the hyperon-nucleon and hyperon-hyperon interaction. Okay, so let's move now to the hyperon-nucleon and hyperon-hyperon interaction and what we know. So if we compare with what we know with nucleon-nucleon, really it's not so much. So if here on this box here, I just wanted to introduce some numbers about scattering, of hyperon-nucleon, and here about hypernuclei. So actually, because these hyperons have this very short lifetime, I mean, imagine the lambda has like lifetime of 10 to minus 10 to 10 to minus 10 seconds, okay? So it's really a very short lifetime, which doesn't allow you to really have, targets and even, have a very low density of beam fluxes. So basically it's very complicated, to create this kind of scattering. So there are other ways, of course, indirect to try to scatter hyperons. And the information that we have as compared to nucleon, it's very limited. So up to actually the discovery of the new techniques, okay, which is called femtoscopy, we have like around even less than 50 data points for the lambda nucleon and sigma nucleon. And for the cascade nucleon, even very few events. Now, for hypernuclei, as I was mentioning before, actually there are like more than 40 lambda hypernuclei. So this already is telling us, of course, that if you can bind, a lambda into nucleus, it means that there is some attraction, okay, between the lambda and the nucleons. Then there are a few lambda hypernuclei. Actually, in the chart before, I think we saw like 3. So this is already telling us that probably the lambda is also attractive, but very weak, okay? And then we have like also a few cascade hypernuclei. So again, this is also telling us that the interaction is attractive. And now for the sigma, it is believed that nucleon is believed it's been repulsive. It seems that there's an evidence for one sigma hypernuclei, but then you have to see really, I put it in question mark. I mean, it seems there is determinations, but then you have to see in which conditions actually, okay? So this is what, we are still dealing with. As you can see, the information is not as much, of course, as nucleon. And with that information, actually, also researchers try to build models, okay, to construct this hyperon-nucleon and hyperon-hyperon interaction. So here I try to summarize a lot of work of a lot of groups, okay, and then I hope, if somebody is not here in this classification that I made myself, so just please just let me know. So basically the people working, on nucleon interactions from researchers from Jülich and Nijmegen, okay, they, of course, with the years, we're talking about the 80s, they already, start building up the interaction of hyperon and nuclear and hyperon, assuming some kind of symmetries, in particularly the SU3 flavor symmetry, okay, because you have up, down, and strange. And this is, as I said, the main 2 groups are Jülich and Nijmegen. And of course, nowadays, I mean, already from the past century, we're having these chiral effective theory approaches that help us, of course, to have a more systematic way, in the sense of having some perturbative expansion and some scale, that or some parameter that allows us to do this perturbative expansion, and therefore to try to build a hyperon-nuclear and hyperon-hyperon interaction in a similar way, or as done for the nucleon. And this is again, one of the main groups is in Jülich, Bonn, Munich. So some of the researchers already working on nucleon, and hyperon-nucleon from the point of view meson exchange are also working on these chiral effective models involving hyperons. So there's a lot of progress in that field nowadays. And of course, there are other ways. I marked those 2 because I'm going to show you some examples of scattering data. But of course, there are other ways that also, or manners, let's say, of building these interactions. So there are quark model potentials. So of course, now you might think the hyperon and nuclear are made by the constituents, okay, by the quarks, and then you can try to explain the interaction by the exchange of mesons, for example, between these quarks. So this is another way of approaching. And there is also another one that it has been very successful for nucleon, these renormalization group techniques in order to build a low momentum potential. It has been very successful because of the amount of data that you have in nucleon that allows, to really have kind of a universal effective interaction and forget in between quotation marks, in the sense that you integrate out the region, the complications of the short range interaction, okay? So for that, in nucleon has been very successful, and people are working on that. But for hyperon, nucleon, hyperon is still something not so clear because the interactions are not so well constrained because of basically you use symmetries and the information data, experimental data is not so, let's say, big, that we don't have such an amount of events as the nucleon. And of course, a way also very interesting, and I indicate here like two big groups, are lattice, okay, the lattice calculations. And I indicate two groups, this whole QCD in Japan, and then NPL QCD, which is also European American collaboration. And they also have tried to solve, you know, hyperon, nucleon, hyperon on the lattice. So you can imagine that is also a very involved calculations involving, of course, these correlators. Of course, I'm not an expert, but I mean, really, there is a lot of progress in that direction. And if you are interested, they definitely should look at these works. I'm just pointing out a few of them, but there is much more of them in the past years. Now, just to show you example, okay, of the lambda nucleon and sigma nucleon scattering. So I'm showing you some results from the meson exchange model, this Jülich. This is one case, and leading order and next to leading order, this will be from these chiral effective approaches. And you, for example, I don't know, you can look at lambda proton going to lambda proton. Here you have sigma protons, and these are cross sections as a function of the momentum in the lab. And you can see how good or bad they do with respect to the data. So for example, on that one, you can see that the blue line was this meson exchange model is not doing bad, at least for the region that we have data here. The other ones, well, you see a band, so this is already taking into account the uncertainties, but as you can see, you know, you would expect that the next to leading order, which is the red one, will be on top of the green one, because you think kind of in a perturbation expansion that the next to leading order should be smaller. But here there are some assumptions in the next to leading order that doesn't allow you to, you know, to really think that in the sense that there are some coupling constants next to leading order. I mean, these are details, okay, but that are not taken, you know, in the same way using some symmetries that is done in the leading order, okay? So this is kind of the disparity in the values. But okay, just to show you that people are working on that and trying to do their best. Of course, some of the data you can see huge error bars. And one of the, let's say, cool things happening, you know, in the past years is these femtoscopy techniques, where basically, you know, they do some correlation functions, which what is a correlation function is kind of a ratio of the relative momenta in what they call uncorrelated pairs of hadrons with respect to non-correlated pairs. And this correlation function, sorry, yes. Somebody talk? No? Okay. If not, I don't see you. So if somebody wants to say something, please talk. So what I'm saying is that this correlation function, it's directly related to the size of the source and also to the scattering length and range of the interaction. And this scattering length and range of the interaction, you can take it out from your theory. And that's why you, for example, see here, these are the data, these points here. And then you see the results coming from, for example, this green one is from a Nijmegen model, soft core, from 2016. This is from Nijmegen soft core from the 97, this yellow band here. And then from chiral effective field theory, you have this one here and next to leading order. So basically you can relate this correlation function with the theory, okay? And in that sense, you can see how good or bad your predictions are. But this is kind of a new techniques that people are developing and analyzing, as I said, for the hyperon nucleon interactions. I only talk about lambda nucleon, sigma nucleon. Also, there is cascade nucleon for those and others. Okay, so but just to give you a bit of an idea. Okay, now hypernuclei. So I just moved now from this two-body system to a few-body system. So we have, as I said before, like around 40 hypernuclei, lambda hypernuclei. There are different ways that those have been produced. So basically, you have a nuclei, and you hit it with something. So here you have strangeness exchange reactions, where you have an strange quark exchange from the meson to the baryon. Okay, so you exchange the strangeness between the meson and the baryon. And the kind of reactions I'm talking about is, a K minuses, which is slowed down until it's taken by the nucleus. And then you have a pion, and then you end up forming a carbon with a lambda. Okay, these are experiments, for example, in Italy, in Finuda, CERN, BNL, or Keck in Japan. There's also associated production reactions where actually you have a beam of pions. Okay, and now what you have here is annihilation of DD bar pairs, in this case with a neutron, and then you form an SS bar. Okay, so these are associated productions. So basically it means that you produce S bar and S at the same time. So you produce anti-strangeness and strangeness. And these kind of reactions are shown here. And the difference between the strangeness exchange and the associate, of course, you can imagine that having pions beams is easier than having kaon beams. Actually, the intensity of those is larger for the pions, but then the cross sections are smaller, as you can imagine, because of this annihilation here. Okay, and then creation again. Now, this is another one, and then, for example, electroproduction. So the idea is that you have an electron coming that will collide, with a proton, and then give rise to an electron leaving and a kaon and a lambda. This reaction, electroproduction, can be understood in terms of this virtual photon interacting with a proton. And again, you can have this kind of, reactions with a carbon, for example. The difference here, of course, with respect to the other ones, it's easier actually to have electron beams, or at least intensity, is higher, but the cross section with respect to the associated production is like 2 times less. Okay, so there's always this competition of how good intense your beam can be and how the production cross sections are. Lambda hypernuclei. Here I show you one possibility, presented by Panda, where you have an antiproton beam colliding with a nucleus, and then you get a cascade, and this cascade is, there's a second nucleus that it takes it, that somehow in the orbital, in atomic orbits, but then it decays, and then giving rise to 2 lambda that binds in the nucleus. Okay, so this is a kind of second step, process in a cascade in a secondary target, and then you can bind 2 lambdas here. And of course, you could also think of these reactions, but not having that, but actually the cascade at the end binding with the nucleus, or reactions, of course, involving K minus proton giving cascade minus and chaos. Okay. Well, other than that, what I want to say is that you now can build get all these nuclei. Again, as I said, those are the first one that I was presenting you. Strangeness exchange, those are electroproduction, those is associated production. And again, I'm just maybe repeating myself, but the idea is that you can get information from the hyperon nucleon, hyperon, and also test your models. Okay, try to test in a few body system, given your interaction, how good or bad they do for predicting the spectroscopy of the different levels, okay, of this nuclei, hypernuclei. So just a couple of examples, the lambda hypernuclei. So there are more than 40. I mean, you can see here, this is the S lambda, P lambda, so different states, okay, of the binding energy of different states as a function of the mass number to the minus 2/3. So you increase the mass number as you go to the left, okay? And the idea here is that these are the experimental data, and this is a model, okay, which shows you kind of this saturation, okay, of about minus 30 MeV of the binding energy of the lambda in a nucleus. So what I'm telling you is this will be kind of the infinite limit, okay, and when you have infinite number of nucleons, so what it will be. And this actually is a famous minus 30 MeV that people, when working, for example, in neutron stars and talk about saturation density, discuss the fact that there is this minus 30 MeV of attraction from the lambdas in nuclei. There is something also interesting lately about what is called the hypertriton lifetime puzzle. And the idea here is the following. The lambda binds, is very weakly bound with nuclei, okay? So this will translate that the wave function of the lambda in a nucleus will not differ much from the wave function itself of free lambdas. And this, what is expected then is that the lifetime, okay, of this hypertriton and the lifetime of the lambda will be of the same lifetime, similar, okay? But there were some experiments, and you can see here several experiments that where the lifetime of the lambda should be somewhere in that, here it is actually, the PDG, so it should be around here. Then you see that some of them were, producing lifetime much smaller experimentally. And this actually triggered very much the interest, in particular with, there was this Alice result on lead that was going in the direction expected, whether the star result, which is here, one of the latest one, was below this expected lifetime. So then actually this triggered a lot of interest from the point of view of experimentalists, but of course also from the theory, just trying to understand this lifetime of the hypertriton, okay? Very good. So let me now say a few words about hyperons in matter. Are you following? Do you have any questions? As you said, you can stop me anytime. And okay. No? Okay. Well, just stop me. So now I'm talking about hyperons in matter. So I was moving, okay, from two-body interactions, hyperon-nucleon and hyperon-hyperon, to a hyperon in a few-body system, because you know that it's finite range. So basically, it will only see a few nucleons. Okay, the interaction, the strong interaction of the hyperon with the nucleon. So you have a few body system. Now I'm moving to an infinite system. Okay, this is an idealization. Okay, this I'm talking about an infinite system. Here I'm showing you some results again based on meson exchange models or effective field theory. And this, what I'm showing is this called the optical potential versus the Fermi momenta, so versus the density of the system. The optical potential, what it's telling us is how a lambda feels in the presence of a many-body system of, in particular, in this case, of nucleons, okay? So it's not what a lambda sees with a nucleon, but with a many-body system made of lots of nucleons, okay? So here you have different predictions as a function of the density, as you can see. And now going back to this minus 30 that I was telling you about, this 30 of binding energy, this would be for this average value of density, this what we call the saturation density, which is the density associated with the average distance between two nucleons in a nuclei. So we are talking about values of 1.3, one around here, 1.35, depends on exact value. So you can see a bit of the disparity of these models, but still you got attraction. And let's say that the leading order and next to leading order calculations are closer to what is expected, around minus 30 MeV. And this is for the lambda, and this is for the sigma. Okay, so for the sigma, you can see this repulsion in this will be the Jülich model, or not, no, sorry, this is, we don't have here the Jülich model, this is just the band of leading order in effective field theory. So you see that we have here some repulsion as we were actually, it is imposed somehow. This is maybe more detail on how it is done, but basically because there is information on this repulsion coming from sigma minor atoms. And this is somehow seen here, okay? Now, but this is not, of course, the whole story, and this is why now we are going to move to neutron stars, is because if this was the case that we have some attraction, then lambdas could appear, you know, reduce its mass. I mean, this will be the main idea, reduce its mass as compared to the free one, and therefore could be more easily, you know, that they appear in neutron stars. I will tell you how they appear, because actually there what matters is the weak interaction. And this is something then that people, of course, has also tried to understand from in dense matter. And actually, this has triggered, of course, the interest also on three-body forces. So for the three-body forces, because I was only talking about two bodies, so now the three-body forces seems to, you know, be needed Also, to get the binding energy of the few nucleons. And also in non-relativistic models, like I was showing, I didn't mention the kind of model that I was plotting on, getting all these plots, but those have problem in getting the nuclear saturation properties in nucleons. So then free bodies seem to be the way to go for those approaches. And here there are some examples of works that have been done only involving lambdas and the effect of this three body. Okay, so now you see the potential of the lambda. This is symmetric matter. This will be neutron matter. And the fact of the three bodies are giving you certain repulsion as we increase in density. Okay, and this repulsive behavior here means that lambdas, okay, will appear later in for example, if we look at neutron matter and neutron stars, this will push the appearance of these lambdas because they will make the interaction repulsive. And this is something that also, of course, has been triggered the interest on neutron stars and lambda hyperons. And this thing here, hyperon partial, I will mention later, but just to put you into context, okay, on what is interesting, to study this lambda in dense matter, because there are scenarios like neutron stars where this might become important. Okay, so this is for the first part of the talk. I think I have like 15 minutes, maybe more, I hope. So I'm going to give you a brief, okay, ideas about neutron stars. Probably most of you know already what these objects are. So they are producing core collapse supernovas. So they come from a very larger star, which was unstable at some point, and it was, and it collapsed. And the remaining was this neutron star here. They are observed usually as pulsar. So this pulsation, this what is called this pharos in English, lighthouse effect. Okay. There's objects which are pretty compact in the sense that general relativity affects matter. So we are talking about objects of 1 to 2 solar masses. And radius is something now big, as I'm telling you, because there are observations of more precise values of the same star with a mass, with a given mass. And you can see that if you do the mass divided by the volume of these objects, you are getting pretty dense objects. So in terms of mass density, maybe 5 to 10 times of saturation density. And well, you can also have pretty high magnetic fields, okay, and temperatures of the order, depending on the evolution, okay, of the star after the supernova. So it really can be rising from 10 to 6, 10 to 11. I just put some values here, okay. But actually, this is a cold object. Why I'm saying it's cold? Because 10 to the 10 Kelvin is 1 MeV. Okay, so if I'm talking about Fermi, comparing it with Fermi levels of few hundreds of MeV, this is a cold object. And what do we know? We have some observations, okay, of masses, several actually. Radius, as I said, they are actually now, it seems really pinning down the mass and the radius, so that's good. Gravitational waves of two binary merge, two neutrons merging, of course, cooling as well. So here I'm just showing you, okay, kind of a very short summary of things, masses. You have actually masses ranging, around this 1.5 solar masses. And the interesting nowadays is put into really high value of masses of the order of 2 solar masses, because I am telling you models have difficulties, okay, in getting these 2 solar masses, okay, that to get out of your model, depending on what you have in the interior, to really understand these 2 solar masses. There is, as I said, radius, these nicer measurements, like in these different analysis, you can see, which is good, that we have some masses, for example, this one around 1.3, 1.4, around 13 kilometers. Then the second pulsar, we're talking about 2 solar masses, and again of radii, not so different actually, from maybe 13, almost 14 kilometers, and 13. You can see still that the values of the errors are a bit bigger. People were hoping to have smaller radius, error, and this is what we are also hoping for next generation, and probably from nicer as well. Of course, we also have information on cooling from usually isolated neutron stars. And here you have effective temperature as a function of the age. And these are observations. And there are different models that, take into account different scenarios for what is in the interior and different cooling mechanisms. And of course, now lately, we have, since this merger in 2017, observed by LIGO and Virgo. So another source, of information on neutron stars, particular to what is called through the tidal deformability for nuclear physics. This is what we use actually. And this also gives us information on the compactness, on the mass and the radius of those objects, but together on the compactness, okay? So this is also pretty interesting scenario, okay? So the theory, at least, has to understand all these observations at the same time. So this is also too ambitious because we always have also as a nuclear physicist, not only to get that, but also nuclear properties at densities that we control in back to Earth. So this is always a complicated issue. So as I said, I'm concentrating on this part here on hyperons, but first of all, let me look at nucleons, okay? Because this is always, when we start from nuclear matter. And here I'm showing you kind of the way of approaching. So it just is a bit of blah, 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 but just that what we need in order to understand all these observations, one of the ingredients, and sometimes is one of the most important one, in particular for masses and radius, is the equation of state. An equation of state, from thermodynamics, is just a relation, okay, a thermodynamic relation that describes the state of matter. So basically what we mean by that is to relate pressure and energy density of the system, or pressure and density, particle density. And for the nuclear equation of state, there are different ways of trying to put the many-body, okay? Let's say, I would say many-body effects. So there is this ab initio approaches, which usually start from two-body or three-body interactions that I was mentioning to you, this hyperon nucleon, well, in this case, it's nucleon, three-body and two-body. And then you put many-body corrections on top of it. How do you do that? You can do variational methods, can do quantum Monte Carlo, you can do diagrammatic expansions, renormalization group methods, lattice methods. So there's different ways of trying, starting from this two-body interaction to build up, a many-body system. The nice thing, for example, thinking, of diagrammatic in that case, is like you have a systematic addition of, larger many-body corrections. The only problem is, for example, up to where this is applicable, okay? Because your diagrams, for example, start getting more and more complicated. You have less control of them. You have many of them. So really at some point it cannot be very complicated, okay? Now you have another way of approaching is like building density dependent functionals that has some parameters that are fitted to nuclear properties and of course also to some observables. And then with that you do predictions, of course. And here I'm showing you non-relativistic density functionals like SCRM, like Gogny, relativistic mean fields, liquid drip model, which is like the same model based as mass formula in nuclear physics for describing nuclei, Thomas Fermi model, statistical models. So the nice thing is that you can apply it to high densities, okay, because you have a parameterization in terms of density. Actually, let's say functionals, not parameterization, functionals. But the point is that you can get lost in the number of parameters that you are and the number of terms you are putting just to improve your description, okay? And then could be also a problem of trying to be too refined and starting to be less predictive, okay? So, and this is just in general, okay? I'm not giving you much details, but I just want you to understand what happens when we get Strangeness into the game, okay? So basically, I didn't say, but the conditions that you have in neutron stars is just weak interaction. So if you only have nucleons, these are the reactions that have to be equilibrium because of the scales of the system, okay? So you have a neutron going to a proton, an electron, and an anti-neutrino. I'm missing here a bar. Proton and electron going to a neutron and a neutrino. And the idea here is that these are the reactions if you think first with having nucleons, but if you put Strangeness into the game, you start putting hyperons, The question is whether these reactions involving hyperons could be, energetically more favorable. And this actually could happen because of the nucleon chemical potential as we increase in density because of interactions is increasing, okay? And actually, most of the models indicate that it's possible at 2 or 3 times saturation density. And this is just an example of the kind of reactions involving lambdas and sigmas, for example, as a hyperon. So the idea is that when is it more favorable to have a hyperon than a nucleon? And this is, for example, seen here as an example. How do you get a lambda or a sigma? So basically, because these relations are mediated by the chemical potentials, okay? So basically having a sigma will be possible when the chemical potential of the electron and the neutron will be equal to the chemical potential of the sigma. And for the lambdas, it will be the chemical potential of the neutron. How do you see that? Well, you just look at these reactions and then just put the chemical potentials of everything, and you will see that these are the relations that you have to be fulfilled to be in equilibrium. If the if the sigmas, you think is the mass, so this is the example. So you have here the mass around 1,200, and at some point, the sum of the chemical potential of the neutron and the electron is increasing in such a way that they meet the mass. And then it's favored to have sigma minuses. So it's favored actually to have this kind of reactions here down involving sigmas. The same can be said for the lambdas, but this case is only the chemical potential of the neutron actually, because actually it's the charge that is making this chemical potential of the electron appear. And with that, you actually can construct the structure, okay, of your star. So these are the particle fractions, and this will be the coordinate of the star. It means that we are moving towards the center as we go to the left in this diagram. And then you start seeing when the particles appear, the neutrons first, then protons and electrons, and then at some point muons or sigmas or lambdas appear when these conditions are fulfilled, okay? Good, so, but what happened with hyperons up here? Well, the idea is that you transform a neutron into a hyperon, okay? And then what happens with the equation of state? The energy per particle, the pressure, okay? What happens? It happens that the equation of state gets softer, okay? It goes down. So basically at the same energy density or particle density, the pressure is lower when we have hyperons. Why is that? Well, the idea is, maybe you think in terms of Fermi seas, is like, you have a nucleon that has transformed into a hyperon. So basically you fix in the same number of particles, you have a new particle with a strangeness. So then you have a new possibilities of states that being populated in the Fermi sea. Okay, so before you have nucleons being populating and then increasing, the Fermi level to populate, this. But now it's suddenly, you have new accessible states, energy levels that you can fill out, okay, and they are lower in energy. So therefore, the total energy of the system is reduced, okay, the pressure of the system is reduced. And what happens with that? So the stars, okay, are in what is called hydrostatic equilibrium. So the pressure is compensating the gravity. This is what it's depicted here by this picture here. So if you have less pressure, you will need less gravity, let's pull from gravity to keep the star, stable. And this means that the mass, which is associated, with this pull, will be less. So you will have smaller masses. And if this is the case, this is what I'm telling you. You can see here that if before we had possibilities of having 2 solar masses, now we are having much less masses. And then we are entering into contradiction with the observations, for example, of these 2 solar masses. And this is actually the hyperon puzzle. The fact that it is probable energetically to have hyperons, okay? And then if this is the case, then it means that the equation of state will get softer. And if it gets softer, it means that the masses of these objects will be less. But then we have observations of 2 solar mass observations. So how can we solve that? So this is the puzzle here. And this is a puzzle, and I'm about to finish, that people have tried to solve, of course, like making stiffer the equation of state. How to do that with stiffer two-body interactions with three body forces. And this is what I was mentioning at the beginning, okay, to have these three body forces. Basically, the idea is to push the appearance of these hyperons to larger densities so the equation of state doesn't get soft too fast, okay? So you have to have a kind of a balance, because also you cannot make it too soft, okay, at the beginning. So if you make it hard at the beginning, then hyperons appear. Then you have to make it not so soft, not so hard. So it is a complicated balance, okay? The idea is, as I said, try to push things, hyperons, to later stages. Then you can also push that by appearance of other particles before, or even not by making them appear because there's a quark condensate, okay? So basically the quark matter, okay? So you have a phase transition, okay, into quark matter. Or even, you know, all the theory, which is based that, which is assuming general relativity, classic quotation mark, general relativity, maybe things can be modified because of this new modified gravity theories, or even in the presence of dark matter, okay? So there is, as I said, the puzzle is there. The puzzle that if you put a new fermion into the system, it will soften your equation of state, and this will make difficult to have predictions of two solar masses. And people are trying to work that out. How can we solve this? So actually, this is my last slide, well, almost last, in the sense that I believe, you know, with these new space missions, with NICER already taking data, and maybe the future of in EXTP with this Chinese European collaboration, we will be able, you know, to really start pinning down the mass and the radius. Okay, this is the mass of the radius of these objects, and having simultaneous measurement of the mass and the radius. These are assumptions. This is just, you know, simulation. Let's imagine we have here, this is not actual data. And these are different equations of state, results for the mass of the radius. These are nucleonic. Those involved in hyperons will be this one. And then those, for example, only quark matter, strange quark matter, will be this form here. So basically, I believe that one way to go, and this is not only me, is just really to have this mass and radius measurements simultaneously to really pin down what's going on inside Neutron Star. But of course, we cannot forget, you know, this multi-messenger astronomy that was really pushed since the you know, observation of this binary neutron star merger. So, and this is kind of the present and future. I mean, just probably my point of view, kind of a really general statements. So basically, there's a lot of experimental and observational and theoretical efforts with hyperons in the lab and also neutron stars. There is a lot of unknown yet, but is it very important to pin down to know the hypernuclear and hyperon interactions to understand hypernuclear physics, hyperons in dense matter, and of course neutron stars. And actually the neutron stars is an excellent place where we can test hyperons at really extreme densities. And I believe, you know, in the hyperon physics should go, of course, hand in hand, particle and nuclear experiments together with X-ray telescopes and X-ray astronomy and multi-messenger astronomy. So thank you very much for your attention. And I'm open to any questions and yeah, anything you want to ask and you don't understand.